Similarly, you've got Mg, which is +2, and it's got more delocalized electrons. You got Al, which is +3, so it has even more delocalized electrons. So why is the metallic bond becoming stronger? It's becoming stronger because, so you're going to have stronger metallic bonds. Why? Because positive ions have higher charge density because they've got a higher charge. So have higher charge density. And there's going to be more delocalized electrons as well. So you're going to have more delocalized electrons as well. So if you have more delocalized electrons, there's going to be stronger attraction. So there's obviously going to be stronger attraction. Between the positive ions and the delocalized electrons. So the strength of the metallic lattice increases because remember the attraction between the metallic lattice is between these delocalized electrons, which are attracting the positive ions are attracting the delocalized electrons, and so on. So that is what a metallic bond is. So if you've got aluminium, the positive ion would have a much greater charge, and there's going to be a lot more delocalized electrons. So is that point clear? This point?
Yes.
Okay. Anna, is this clear?
Yes, sir.
So then you have another issue, which is that they might ask you, why is there such a large difference between the melting points of Na and Mg and such a small difference between Mg and Al? Why is it a linear graph? And the reason for that is that when you move from Na to Mg, right, what happens? The charge doubles, right? So the charge on the ions, so the charge on the ions and the number of delocalized electrons, they double, which is why there's such a huge difference between the melting points of, which is why there's such a huge difference between the melting points of Na and Mg. But why not between Mg and Al? Now, when you move from Mg to Al, the charge is not doubling, but it only increases by 50%. So now it's not really doubling. So when you move from Mg to Al, so you can say the charge increases, the charge and the number of delocalized and the number of delocalized electrons increases by 50% only. It doesn't double. Over here, in the first scenario, they increased by 100%. So which is why the strength of the metallic lattice increased a lot. But when you move from Mg to Al, it doesn't increase by a lot, not by the same amount. So the melting points are kind of similar for Mg and Al, but Na is a lot weaker. Is this clear?
Yes. Yes, sir.
So then we're going to talk about silicon. What's wrong with silicon? So we can write this over here. So why does silicon occupies the highest place in the melting point graph? Why? Because it's got a huge macromolecular structure. This is what silicon looks like. So we can just copy paste the structure of silicon. So it's a giant covalent structure. So we can just Google it. I'm just going to paste this. So this is what silicon has, exactly or kind of the same structure as diamond. So it's got roughly the same structure as that of diamond. So I placed it there, and so kind of the same structure as diamond. So let me draw an arrow. So it's got a giant covalent structure, same as diamond. So there's a large network of very strong bonds that need to be broken. Of very strong bonds need to be broken. So same thing as diamond. That requires a lot of energy. So the melting point is really high. Now, what happens to these last ones, the phosphorus molecule, P4S8 and Cl2 and argon? What do they have? I mean, they're simple molecular structures. Simple molecule means that they are simple molecules. So I can do that one over here. So these ones are simple molecules, which means, like, you know that you've got a Cl2 molecule, which is this, and you got another Cl2 molecule. Can you tell me what intermolecular force do they have? I mean, simple molecules have three types of intermolecular forces. There's van der Waals forces, there's permanent dipoles, and there's hydrogen bonding. So, क्या होगा इसमें? What force exists between them?
ID.
ठीक है, so it's going to be instantaneous dipole, induced dipole, because it's a non-polar molecule. Because there is no difference in electronegativity, so the electrons are going to be evenly distributed between the two atoms. So you got weak van der Waals forces. Which is basically instantaneous dipole, induced dipole. And these forces are present in all the molecules, like in a P4 molecule. In a P4 molecule, you got this thing. Like a P4 molecule is like this. So a P4 molecule is something like this. Let me just trying to draw a three-dimensional molecule. Just a second. So let's do this. And here's another P. So the P4 molecule is every phosphorus trying to make 3 bonds. So it's something like this, like a pyramid, with a 3-sided base. That is what a P4 molecule looks like. Every phosphorus is making 3 bonds. And you'll have another phosphorus molecule. Both of these molecules are going to be, they're going to be non-polar. Because it's only phosphorus. There's no difference in electronegativity. So they're non-polar. They're going to have van der Waals forces as well, or induced dipole, instantaneous and induced dipoles. Same goes for the S8 molecule. So sulfur molecule is this thing. I'll just copy this. So the sulfur molecule is usually S8. It's 8 sulfur atoms. They're bonded to each other. So I'll just draw it. So it's basically 8 sulfurs, all bonded to each other. So that's 1, 2, I got 3, 4, 5, 6, and we can have 7 and 8. Each sulfur atom is making making 2 bonds. So again, it's a non-polar molecule. It's a big molecule, but it's non-polar. It's a non-polar molecule, and again, they're going to be just van der Waals forces between them. So the point is, they all have weak van der Waals forces. And the last one is argon. Argon is just an atom. It doesn't form a molecule. So it's also non-polar. It's just one atom. And argon is also going to have weak van der Waals forces between them. So अब ये बताओ कि which one has the greatest van der Waals forces? What factor does the van der Waals forces depend on?
I think it's sulfur because it has more surface area.
And it's a bigger molecule. Remember van der Waals forces? I mean, van der Waals forces are going to be stronger. I mean, all of them have van der Waals forces. But remember this, that van der Waals forces, I mean, they depend on surface area as well, but obviously the number one factor is the size. So van der Waals forces, bigger molecules have more van der Waals forces. You get more van der Waals forces. So sulfur has so they're going to ask you about this as well. So remember this, sulfur has the strongest van der Waals forces out of all of them. So out of all of them, sulfur is going to have the strongest van der Waals forces. And the weakest are going to, argon is going to have the weakest van der Waals forces because it's the smallest atom. So they'll ask you about this. So remember this, that why do these molecules have such low melting and boiling points? Why? Because they have van der Waals forces. The simple molecule, they've got temporary dipole-induced dipoles, which increase with size. So S8 is the biggest molecule. Phosphorus is the smallest molecule. Is that clear?
Yes.
There's another thing that a lot of elements actually have allotropes. Just like carbon, carbon can exist in many forms. I mean, even phosphorus has a lot of allotropes as well. Like if you so all these nonmetals, for example, there are 3 allotropic forms of phosphorus: white phosphorus, red phosphorus, and black phosphorus. So they're not going to have the same melting point. Exactly the same way as graphite and diamond, they don't have the same melting point. So just remember the melting points are not exactly the same. Like if we can have a look. The one that I drew was one form of phosphorus. If I can. So it was just one form of phosphorus, which is commonly known as red phosphorus. That's the most common one. So yeah, I drew the white phosphorus one. The red phosphorus is the polymeric form of the same one. There's violet phosphorus, there's blue phosphorus, there's black phosphorus. So I mean, there's diphosphorus as well, which is 2 phosphorus atoms, just like a nitrogen molecule, forming a triple bond. So you got all these different arrangements. Like phosphorus can exist in a lot of different forms. The most common ones are these 2. And remember, diamond also doesn't really exist in just 2 forms. It exists in a lot of forms. It can form carbon nanotubes, a lot of different structures. So each one is going to have a different melting point and boiling point as well. But so the one that we are talking about is the most common one, which is P4. We're talking about white phosphorus. So just remember and also for sulfur. I mean, sulfur allotropes. So you can see there are lots of different versions of sulfur. This is the most common one, which is S8. But for sulfur, there's a lot. Like there's S5, there's S6, there's S7, S8. So you got lots and lots of different versions of sulfur. Is this point clear?
Yes.
Yeah, chlorine is the one that I don't think chlorine has a lot of. I mean, atoms that make many bonds, like carbon makes 4 bonds, that they can exist in many different forms. I don't think chlorine has a lot of allotropes actually. I mean, the most common one is just Cl2, but I don't think yep, it does not exist in allotropic form. So chlorine doesn't. I mean, remember, there's a reason why chlorine doesn't form allotropes because it only makes 1 bond. So the structure would kind of end over there. Like if it makes 1 bond with Cl with another Cl, that's it. I mean, it doesn't need to make any other bond. So which is why chlorine is obviously not going to make or it's not going to have different structures. So keep this in mind that non-metals, if they're making a lot of bonds, they always exist in many different forms. So so the ones that we are talking about is specifically P4S8, the more common one, Cl2 and argon. Then you've got electric conduction. So it's obvious that the first 3 are metals, so they're good conductors of electricity. You should know the reason. It's they got delocalized electrons. That's why. Non-metals are obviously not going to conduct electricity. They're covalent molecules. They're poor conductors. They don't have delocalized electrons. The rest is about their reactions with. So most of the stuff is just memorization from now on. For example, sodium reacts with water. Now, you should know that in O-levels, you got a lot of questions about sodium reacting with water. So sodium, it reacts with water. It has a vigorous reaction, a very vigorous reaction, and a very strong alkali is formed, and hydrogen gas is formed. I mean, you might be asked about the observation for this particular reaction. Like, I mean, you should know. Like, I can add the observations over here. So you should know about this is that sodium. What is sodium? Sodium is a soft metal. It's a soft metal. And it's also low density. Which means that it's going to float and fizz on the surface. So when you add it to water, sodium floats and fizzes on the surface. And it's a vigorous reaction. It might catch fire, it might melt, it might become red hot because it's a vigorous reaction. Is this clear?
Yes.
अच्छा फिर ये कि you've got Mg with H2O. Now Mg with H2O is it's a very slow reaction. It requires a high temperature. I mean, most of the time, it's got to be steam. Mg reacts with steam. You need steam to react with it because otherwise with cold water, it's a very slow reaction. It will happen, but it will be a very, very slow reaction.
Sir?
Yes.
Are we not doing energetics?
We're doing energetics at 8:45.
But isn't this the same code for the 8:45 class?
This one?
Yeah, because I'm really confused. I have 2 of your classes going on and half of my topics, most of my topics are left in half because I keep switching.
I think you should just keep with that one.
But aren't you guys already ahead of me in that one?
Not in that one. We started energetics. We just started energetics, right? You haven't done energetics, right, Anya?
What topics have you done in the other class?
The only thing that we did was moles. So we pretty much,
okay,
I mean, this one, the thing with this one is that this class was supposed to end in because most of the people in this class were actually giving the exams in October, November, and they've actually given the exams, most of them. Okay, so we are only left with, I'm just doing completing inorganic, which was left over here. Okay. So
the thing that we did with alcohols and carboxylic acids,
yeah,
was that organic or was that inorganic?
no, that was organic.
Oh, could you send me the recordings that I've missed?
For the organic, what I'll do
Yeah.
is just one second.
Because you sent me this one link that had all the videos and I couldn't seem to find any.
Just one second. As for this one, I'll keep updating. Like, if you have time, you should do inorganic in this class as well. Just one second. So let me quickly.
Yeah, I've got that.
Just a second. As I'm sending you one link, but I'm sending everyone one link. This covers, it's a 1 hour lecture that covers the entire organic chemistry.
Because I'd like to just get the recordings of the ones I've missed so I can catch up with you guys.
Okay. I mean, this one, I'm going to, even in this class, I will go through organic because we had to sort of hurry up because everyone was having an exam. So kind of things got messed up. But even in this one, we'll try and go back to organic and we'll try and do more past paper questions on that. Okay.
And is this your first class of inorganic?
Inorganic, yes. I mean, you'll probably be done with this in like 3-4 classes because most of it is just memorization. You don't have to really know a lot of stuff. I mean, I'll just quickly tell you, like the first thing that we just discussed was, like, you have to discuss a lot of things about period 3. So the first thing that we just discussed or talked about was the melting points of period 3 elements, right? So it's just that you have NaMg and Al, they're metallic. So they've got metallic bonds. So Na does not have a very high. So this is what metallic bonds look like. I mean, you already did that in O levels. So why is Na having a lesser boiling point, melting point compared to Al? Why is Al a stronger metal? And the reason is that metallic bonds are positive ions attracting the delocalized electrons, which are then attracting the positive ions. So they're all attracting each other. So Al has more delocalized electrons and it's got a greater positive charge. So there's more attraction. So that's why the melting points continuously increase. Then we talked about silicon. Why is silicon having such a high melting point? Because it's a giant covalent structure similar to diamond. That's it. And then we talked about why do phosphorus, sulfur, and chlorine and argon have less boiling points or melting points? Because they're simple molecules. Simple molecules having weak van der Waals forces or weak intermolecular forces. So Cl2 molecule, another Cl2 molecule, they're simple molecules, small molecules. They don't attract each other very strongly. So they've got weak van der Waals forces, which increase with size. Okay. Hani, is this clear?
Yes, sir.
And these are the molecules. Like Cl is in the molecular form of Cl, mostly Cl2, phosphorus is P4, sulfur is S8, and argon is Ar. I mean, argon doesn't bond with anything. So, and then electricity conduction, the first 3 are good conductors of electricity. So why? Because they're obviously metals and they've got delocalized electrons. You can add that over here. I mean, they might ask you. So they got delocalized electrons. I said then the other ones are non-metals. They don't have delocalized electrons. And then we started with the reactions with water. So we talked about Na. Just like in O levels, Na sodium has a vigorous explosive reaction. It's a soft metal with low density. You can cut it with a knife, but it's extremely reactive. You have to store it in oil. So when you react it with water, add it to water, you get an explosive, vigorous reaction. And sodium does not sink. It's got low density, so it floats and fizzes on the surface. That's it. Mg preferably reacts with steam. Mg is not very reactive. It requires high temperatures. Sodium forms a strong alkali. It forms NaOH, which is very soluble. Mg does not form a strong alkali. Why? Because MgOH2 is insoluble. I mean, I can add that. I mean, you should know the solubility. So this one.
Can you explain the alkali thing again, please?
Just a second. Remember, NaOH is very soluble. Group 1 compounds are really soluble. So NaOH, when you mix it in water, what will happen to it? It will dissociate and ionize and produce a lot of OH ions, right? I mean, so for example, I've got a beaker over here, and in that beaker, I've got NaOH. I mean, the first reaction, NaOH is forming, right? So NaOH is really soluble. So it will mix with water and produce a lot of OH ions and Na+1 ions. Right, so a lot of OH ions are going to be produced, which means it's going to be a strong alkali. What if magnesium hydroxide is formed? The problem with magnesium hydroxide is most of it is insoluble. So if MgOH2 is formed, it's not going to dissolve. It's not going to dissociate. It's not going to produce a lot of Mg ions and OH ions. Is this point clear?
Yes.
Is MgOH a solid?
It is a solid. It's not very soluble. So remember the solubility of compounds. I can open a sheet where the solubility of, I can add that over here. Just a second. Where's the O-levels thing? Just a second. So revision data sheet as a business solves. So I'll just copy paste it over here. So this one, remember this solubility table? This needs to be remembered. So I'm just going to copy paste it here. So this thing. Remember this, hydroxides. So group 1, and it is 4+1 oxides and hydroxides are the ones that are soluble, and some in group 2, that's it. The others are all insoluble. So magnesium hydroxide, not soluble. So which is why magnesium hydroxide is, if you add it to solution, it's probably going to just remain as MgOH2 as a solid sitting at the bottom. It's not going to dissolve and mix with water and produce these ions. Hania, is this clear?
Yes, sir.
So we'll refer to, I've pasted the solubility table over here, so we'll refer to that later. Now aluminium does not react with water, and it has absolutely no reaction with water, even though it is kind of reactive. But and the reason is you studied this in O-levels a lot. In O-levels, you studied about aluminium, that aluminium has this non-porous, unreactive Al2O3 coating on top of it, which protects it. Do you remember that? That what happens is that if you have aluminium, then just like iron rusting, aluminium does the same. A block of aluminium, it will quickly get coated with rust in the form of aluminium oxide. So it will develop a coating very quickly, and it's a lot more reactive than iron. So it develops that coating very quickly, and it forms this rust, which is Al2O3. But unlike the rust of iron, the oxide of iron, which is powdery and reddish in color, aluminium oxide is really tough, and it forms this very strong coating that kind of seals or covers the aluminium very quickly. Is that clear?
Yes.
Okay. Hania, is this clear? Anna, clear?
Yes.
So that's about aluminium.
Sure.
Then you've got silicon. It does not react with water, no reaction. The others, they don't react with water. Like silicon is a giant covalent structure, just like diamond. It obviously doesn't react with water because you would have to break a lot of bonds. Cl2 does react with water. You add it to swimming pools and it forms chloric 1 acid and hydrochloric acid. These two things are produced. So you just have to remember the reaction. Then about oxidation states, you should know Na is +1, Mg is +2, Al is always +3. Silicon is usually +4. Phosphorus can have multiple oxidation states like +3, +5. A lot of non-metals, they usually have multiple oxidation states. They can have many different oxidation states. Same with Cl. Cl can have multiple different oxidation states. And I gave examples of compounds. And I'll briefly comment on this as well. That, why do non-metals have multiple oxidation states? And the reason for that is, let's talk about Cl. The reason is that they are very flexible with their bonds. Like if you talk about Cl, the electronic configuration of Cl is, it's 3s2. I mean, it's outer shell, 3px, 3py, and 3pz. So it's 2, 2, and 1. So how many electrons does it need at the moment? Which orbital needs an electron? Quickly tell me.
3pz.
Okay, so it needs 1 electron over here. So how many bonds would it make? It would make just 1 bond, right? So it would make a bond with, it will pull an electron from H and bond with it, right? It's going to try and fill this orbital. So that's 1 bond. But then the thing is that in the third shell, you've got a lot of other orbitals. The third shell is really big. So what happens is there's a 3D subshell present as well. Remember the third shell can have a maximum of 18 electrons. So you've got this lots of 3D orbitals as well. And so on. So remember the octet rule only applies to the atoms in the second shell, like up till period 2. After period 2, period 3 atoms are bigger in size. So what can happen is that Cl can expand its octet. Instead of having 2 electrons over here, it can send 1 electron further up. So now how many bonds can it make? It can attract, or it can bond with 3 hydrogens. Like it can, this Cl over here, it has distributed its electron. It can distribute its electron even further because it's got a much bigger shell. So it can have 1 over here, 1 over here. And how many bonds can it make now? It can make 5. And similarly, it can also just keep 1 electron over here and further distribute its electrons. Now it can bond with 7 different atoms. So the point I'm trying to make here is that the third shell, like you can visualize it like this, that the third shell is really big. Cl initially had electrons like this. The electrons were all packed up in these first few orbitals, right? But the third shell is much bigger in size. At the moment, only this electron or this particular orbital can bond with an atom because that's the only one that's empty. But what it can do is, because the third shell is so big, it can accommodate 18 electrons in total. So Cl can kind of distribute electrons like all over the place and bond with more atoms. It can bond with an F atom over here. It can bond with an F atom over here. Like fluorine needs electrons, so it can bond with 7 different fluorine atoms. So it has variable oxidation states. So there's a lot of flexibility in the way it's able to bond. So remember, the basic idea is Cl is an electronegative element. It tries to pull electrons from other atoms and other atoms try to pull electrons away from it. But since Cl's outer shell is a lot bigger, it's got a maximum capacity of 18 electrons. So there's a lot of variability. It can attract 3 electrons from 3 atoms. It can attract 5 electrons from 5 atoms. The shell is much bigger. That is not the case for second period elements. Like if you talk about fluorine, The second shell of fluorine is maximum 8 electrons, that's it. So fluorine doesn't have that variability. It can't have multiple oxidation states, but chlorine can. Is this point clear?
Yes.
Yes,
Yes,
sir.
sir.
Okay. So just remember that when you look at the periodic table, remember that the octet rule ends at period number 2. I mean, after that, after period number 2, the atom, it's up to the atom. Like, it's up to its ability to attract electrons. Like if its nucleus is capable of attracting 10 electrons from 10 atoms, then it will do that. If its nucleus is not capable or not strong enough to attract electrons from other atoms, it's going to attract fewer electrons, right? But the shell is much bigger. Like, you're not running out of space in period number 3. So it's up to the atom, like how many electrons can it accommodate? So the same thing goes for sulfur. Like sulfur can gain 2 electrons and form -2. Sulfur can bond with 4 atoms. It can bond with 6 atoms. So sulfur can have a maximum of 18 electrons. So it can have multiple oxidation states. Same with phosphorus. Nitrogen cannot, but phosphorus will. So let's continue from here. Multiple oxidation. Hopefully this is clear. You should remember. This will continue tomorrow then, okay?
Okay, Allah Hafiz. Thank you.
Okay, take care.
Thank you.
If you have time, could you please send me the previous recordings as well?
For this one?
For organic chemistry and then inorganic.
Okay, I've sent
Like
you one.
Yeah.
I've sent you one for organic.
Yeah. But that one's everything in one video, so it might be more rushed and not detailed.
Okay.
Thank you.
I'll do that. I'll try and do that. Okay.
Thank you. Allah Hafiz.
Okay, take care. Allah Hafiz.